All right, we're going to go ahead and get started. This video is an intro to basically linear graphing 2. So on Tuesday we did linear graphing 1. I also explained on Tuesday that this coming Tuesday, which is about 5 days from now or whatever, I will not be able to attend the lab at 8 a.m. On that Tuesday like I'm normally supposed to. I'm taking a friend to a doctor. So I've got to take care of that, but I don't know yet whether I'll make the video earlier than 8 in the morning and just have it posted by 8, or if I'll do it later that afternoon. But the main thing is, I'm not necessarily going to be able to do it in a public at a public time or a time where everybody can see it. So it might be late at night, it might be early in the morning or something like that. So I'll just post the video as soon as it's done. It'll be posted on my YouTube channel. I'll also make an announcement or an email to everyone just to let them know when it's there. So that next week's lab on Tuesday will be posted. It's just I won't have open attendance. So that's just a reminder. This week's lab is on linear graphing 2. So the first week, I mean, or excuse me, Tuesdays was linear graphing 1. And we're just learning techniques of taking relationships, functional relationships that we are in some sense discovering for certain variables. And we're figuring out ways to make them graphs that are linear. The main reason being that when you use a linear graph, there's a very easy mechanism that, well, I shouldn't say easy. There is a straightforward mechanism for finding a line of best fit, and it's called the least squares fit. Now, you can do that least squares fit on every other function as well, or just about every other function as well. The problem is sometimes when you do it, and other than linear expressions, sometimes you get an error that grows exponentially, all sorts of weird stuff like that. So what we ideally try to do is make plots of our y variable, whatever we want to put on the y-axis, we'll put a plot of that to raise to some power, or we'll put a plot of whatever we're going to put on the x-axis. We'll put that variable raised to some power, or we might do both. Sometimes we'll, raise the y-axis power, or raise the y-axis variable to some power, say 3, and then the x-axis variable will raise it to some power, say 2, or something like that. And what we do is we try all those different options, basically, all the variations of the exponent in y as well as all the variations of the exponent in x until we find a single line of best fit. And then that becomes, y to the m power is equal to m, the slope, times x to the q power plus b. So by doing it that way, you get a linear expression y equals mx plus b, but y is actually y to the n power, and x is actually x to the q power. So that's mainly what we're trying to show you here. And this is not something that we're just making up just because that's the technology that we have or whatever. This was pretty much the way Kepler did it as well. For instance, when Kepler was trying to figure out something about the planets of the orbits of the planets, what he did was make a plot of the period of the planets, which you knew, versus the length or the semi-major axis, which is sort of like the average distance between the sun and the planet's orbit. If you made a plot of that period on one axis and a plot of that semi-major axis on another axis, and when you do that, it didn't come out linear. So then you'd try, okay, well, let's take the period raised to the 2 power. Let's try the period raised to the 1/2 power. Let's try the period raised to the 1.5 power. Let's try the period raised to the 3rd power. Let's try the period raised to the 3.5 power, and so on and so forth. If none of those gave a straight line, then he would try, okay, well, let's try the period on the vertical axis to the 1 power, but let's try the semi-major axis to the 2 power, or the semi-major axis to the 1/2 power, or the semi-major axis to the 3/2 power, to the 3 power. If none of those gave actual straight line graphs, then you'd try doing both. You try y to the 2 power and x to the 1 power, y to the 2 power and x to the 1.5 power, y to the 2 power and x to the 3 power, and keep on trying that. Once you ran out of what you could do with the various x's, then you change the y again. So now you're going to do y to the 3rd power and x to the 2 power, x to the 1.5 power, x to the 1/2 power. But by doing both of those, you're getting all the different possibilities. And of course, we don't try every power historically we've seen that the exponents that seem reasonable in physical contexts are usually one halves, which would be a square root, or one thirds, which would be a cube root, or squared, or cubed, or to the fourth power, stuff like that. So we've found that most of the time nature just gives us laws like that with very reasonable exponents. Like I said, one half power, two halves power, three halves power, four halves power, all those different powers. And then sometimes we even get something weird, which ultimately is what turned out with Kepler's third law. The square of the period is proportional to the cube of the semi-major axis. So you could, for instance, have plotted the semi-major axis on the horizontal scale, call it A, and then you plot the period, call it T, on the vertical scale. And what he ended up finding out was the right correlation to give him a straight line was the period raised to the square power, to the two power, and the semi-major axis raised to the third power. And with that, he got a straight line, and that became Kepler's third law. So that's what we're trying to do here with linear graphing 1 and linear graphing 2 is showing you various techniques to make equations that aren't linear. Another way that we can do that is, of course, making the logarithm of the equation. So you can take the log of both sides of y equals mx plus b, or of, y to the n power equals m times x to the q power plus b, and you can take the log of both sides of that, or you can do exponentials. There's all sorts of different ways that you can do these graphs, but we're just showing you some of the ways. So that's really what this lab is about: is taking various variables, plotting them for physical phenomena, and then finding a linear fit by adjusting the exponents on the variables. So let me go ahead and show you my screen so you'll know what we're working on. So this is the screen. I'm going specifically to this one and just make sure I'm in the right course. Yeah, there it is. So if we go down to this week's lab, which is lab 4, week 4 lab module, you'll see there's the Tuesday lab. This is what we're doing this week, so, or this lab. So this is that video where I introduce it. By the way, it's like almost 30 minutes long, this video. The first minute and a half is these are back before I was able to edit videos very well, so I just left them as is. So you normally have to, fast forward through the first minute and a half, and they're actually all have the chat on the side. So and it actually has the verbal representation of everything I said over on the side when you're watching this video, so you can even read what I'm saying in real time. So that's kind of helpful. But the main thing is you will have to fast forward it, usually on the order of a minute, maybe even 2 minutes, and then you'll find out that the discussion of the video or the discussion of the lab is really not that long, because the end of the video is packed full of people that happen to come into my Zoom session and ask questions, just like I do now when I do a Zoom video of a class. At the end of that Zoom video, I just treat it like an office hour, so anybody from any class can come in. So you'll see people asking questions about other labs and stuff like that. So don't feel obligated to watch the whole thing. This is just my original statement of introduction for the lab and what we were doing, sort of saying a lot of the things I just said. Okay, so in some sense, you don't necessarily have to watch this at all, but if you want a better explanation or a more thorough explanation, then you can go back and watch that. I think I've done plenty here, but I still give you that as an option. This is the actual lab we're doing, and this is the addendum that we use to make it be able to be done at home. These are the videos that allow you to see the collection of the data, because, as I said, these some of these labs are more or less us doing the lab for you via video and then giving you the data and then you analyzing it. So it doesn't make much sense to try to analyze data on labs that you don't understand how they work. So we've actually made the Lab 6 acceleration of gravity and the Lab 6 kinetic friction videos available as well. So these are the original videos that Dr. Wright and me and Mr. Brune and all of us students, Kevin Mitchell as well, put together when the COVID pandemic hit. So literally that very first semester when the COVID pandemic hit, we had to stop right in the middle of the semester. Everybody had to socially distance. Everybody had to wear masks. Everybody was trying to stay 6 feet away, but we still met on days that, students weren't allowed on campus, and we just did all the labs one by one by one, videoed them one by one by one, and then assign them for the whole semester. So that's what's going on here. This is where you'll turn in the lab. Again, if I find one of those comments documents that you can look at before you turn it in, I'll post it here. I didn't see any just now, so they might be in one of my old labs. That's the same thing with last time. I never found one for that either. But anyways, when you're done, as always, you're going to take your document, which was a PD or was a Word document, and you're going to insert all the sample calculations, all the tables of data. You're going to type in all of the data into the tables. If you do type them, then that means you need to use a font that's different than black, because anything that you type into this document has to be a font color other than black, so that I can immediately recognize what you put in versus what was in the document to begin with. That's the whole purpose of that, typing in a font other than black. You can, however, take those tables, print them out, or electronically handwrite the data into the table as long as it's legible for me. That would be a fine as well. And in that case, I can see it's handwritten, so it's clearly not something that was originally there. So you can even leave it back black. It's not a problem. Okay. But anyways, you have to put in your sample calcs. Those two can be hand done. You could, in principle, use the equation editor in Word, but that really takes a lot of time, and I see no need for you doing that except if you just want to. Okay, so I don't want you to spend any more time than you have to. But if if you got a little OCD thing going, or you like the creativity side of it, and you want to basically use the equation editor to put in sample calcs, that's perfectly fine. You just don't have to. Once you put in that, and once you answer all the questions, remember, any question asked within the lab manual or within the lab document, this document right here, if there's a question, then you're supposed to put your cursor to the right of the question mark, hit return, 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 then click back up in the middle of that white space and type in your answer in a font color other than black. That means every question in the lab manual. Not only that, you're also required to do one sample calc of every type. So, for instance, if you have to take three pieces of data and take the average of them, then that's one of the times in which you have to do an average calculation. So you need to show me one of those sample calcs. But if you have to do that average, 15 different times with 15 different variables, then you don't still show another one and another one and another one. Calculating an average is a sample calc, period. It doesn't matter that it's an average of one thing and then the other one's an average of another thing and the other one's an average of another thing. That doesn't matter. I just need one of those sample calc. Same thing with a percent error calculation. I need to see one. If there's a percent difference calculation, I need to see one. If you have to divide mass by velocity one time, I need to see one of those calculations. If you have to divide a number by 10, I need to see one of those calculations. So every type of calculation you do, you got to show me one sample calc of it. And again, you can completely do that handwritten, and wherever that calculation is called for, sometimes they'll explicitly say, show me a sample calc, or show a sample calculation right here. That's where you want to insert that sample calculation, right there where it is. You don't save everything to the end. You don't save all your graphs for the end either. You don't save your data tables for the end either. Everything goes exactly where it's either required for you to do according to the lab report, or where they explicitly tell you where to do it. So you want it right there in the location that it's called for or that it's needed. Additionally, when you put these things in, you need to make sure that they're big enough where I can read. So sometimes a student will say, okay, I'll take a screenshot of this data table with the graph next to it. And then when they insert it in the page, which is already shrunk by, the margins, which are a bare minimum half inch on every side, when you shrink it down, then all of a sudden I won't be able to read the numbers or something like that. That would be a problem. So I'd rather you take up more white space by having one picture of the data table and then another picture of the graph in whichever order you do, doesn't matter. But having them above each other allows you to make them big enough where they can take up a large fraction of the page by itself, as opposed to each of them sharing the width of the page. So that's just so that I can read things and make out what your data is, and what your graphs were, what your equations of best fit were, and so on and so forth. Now, once all that stuff's been inserted into the lab manual document that I gave you as Word, then you're going to save it as a PDF. Well, first you'll save it with your name in the title, or in the file name, and then you're going to save it as a PDF, and that's what you're going to turn in is a single PDF document, and you turn it in right here. And the due date is June 18th. That's a week from today, but it's at 11:59 p.m. So let me show you what the addendum is, just so you'll have an idea. Uh, Maybe there it is. So if you look at the lab addendum, you can see it says view the video to see how the data was gathered. That's specifically the other two videos that I showed you. The one that says, well, actually, let me check real quick. No, it's not that. That's right. I have to go back to the modules. So let me open this one. So when I'm saying watching these videos, I think you already know which one I'm talking about, but just to make sure there's clarity on this so everybody understands. When I say watch the video, how the data is collected, I'm talking about this Lab 6 acceleration of gravity and this Lab 6 kinetic friction. That's what I'm talking about far as the lab goes. Here it is. So when it says view the video to see how the data was gathered, that's the videos I was talking about. It says complete the lab as instructed in lab book, but use the data below instead of gathering it yourself. So this is the density data that we found for the objects. For the cylinder, we found a mass of 61.32 grams. We found a diameter of 1.92 centimeters and a length of 7.64. That is for a cylinder made of aluminum. Then we had a rectangular block with a length, width, and height of 3.15, 3.15, 3.15. Another block that was 2.54, 1.27, 4.87, and another block which was 1.27, 1.27, 1.27. And then we have the masses there. So we're going to make a plot, ideally, of mass on one axis and volume on the other axis, and then a line of best fit will have a slope that's y equals mx plus b. It'll have that m, the slope, being equal to the density. So that alone should be enough to tell you what variable you're going to put on the vertical axis and what variable you're going to put on the horizontal axis. That's one of the things you should already know. If you don't, it's a good time to learn it. So think about when I plot something on the vertical axis and then a different variable on the horizontal axis. The thing on the vertical axis has a specific unit. The thing on the horizontal axis has a specific unit, and then those two numbers or those two sets of numbers can be used to calculate the slope. You might remember the formula rise over run. Uh, and given that, that can tell you exactly what the units of the slope are. And if those units come out to be the quantity that you want, then you've done it right. So, for instance, we want the density of aluminum. So, density is, for instance, the density of water is 1,000 kilograms per cubic meter. So, the density had units of kilograms in the numerator and cubic meter in the denominator. So, how does that tell you anything about what variables should be plotted on the vertical axis and what variables should be plotted on the horizontal axis? I'm leaving that as an open question because hopefully you already know, but if you don't, I want you to figure it out for yourself rather than just me tell you. Then there's the kinetic friction data, which you also have a video for. And here's the trials for certain masses. And of course, what it means is this point 0.4, well, that's really bad. I just realized that the mass wasn't listed here with its units, and the distances here were not listed as units either. That's not good. We're not supposed to do that. If memory serves me, the point 0.4 is kilograms, and the 1.196 I want to say was meters. Uh, but I might be even wrong on that. It might have been velocity or something like that. But the main thing is whatever that unit is in the SI, that's what these units should be. I apologize. I've got to fix this. I can't believe I never noticed it before that we didn't have the actual units listed up here like we do with that one. So I apologize. It might even be that these are grams, but I can't imagine the mass was so small that it was grams. But I think from the context of the lab manual, when you're reading it, you'll see exactly what these quantities are. So don't. I know it's not a dangerous thing. It's just really, really bad and not professional for us to release a document like this without having the unit. So I apologize for that. All right, now I'm going to go back to the module, and you can see that we've now covered what's in the addendum. I've told you about these two videos. Those two videos will also, of course, give you an idea what the units are. Not only that, I noticed, for instance, in this video, I showed the data that we were using and stuff of that sort. So you can look back there, and that might give you some information. But literally, this video, unless you want to, use it like a office hour learning edition, because you could actually look at it and watch where students are asking questions and I'm answering them. I don't remember what the questions were. If they asked, I know they didn't ask just lab questions. Let's put it that way. So there is some lecture questions in there. I'm not sure what topic it was on or whatever because I didn't watch the whole thing over again. But that's it. That's what you've got to do this semester. And of course, like always, or this second lab of this week. And just like always, you're going to turn this in here. And you can see it only takes a file type of a PDF. It should be exactly one document. I don't, in fact, you're going to lose points if you turn in multiple documents for one lab. Now, if you turn in the lab document as a PDF and then a day later, 2 days later, 3 days later, or something, you realize you made some kind of mistake, then you can just resubmit a corrected version. And I'm always going to read the last document that's been posted. That's not going to count against you, even if it comes in after the due date. Again, if it's up there by the time I grade it, then I'm not going to mark it as late. So that gives you a little bit extra time. But the main thing is, if you actually do that, then you just want to make sure you post a newer version, and that newer version is what I'm going to read. But again, it should be exactly one document, not one document with the lab manual write up that I gave you in Word, but now in PDF. And then after that, you don't have a separate file that's some of the graph data or some of the graphs or anything like that. It should be one file for me to read one time. You will lose points if you don't do that. So if you look at this, by the way, you can see that there it was. I was going to say you can see what the due date is, but the due date is June 18th at 11:59 p.m. So that's it. I hope that explains it well enough. Of course, as always, you're welcome to send me a text message or an email. Text message, of course, I'm usually able to respond to quickly, more quickly. So also remember, if you do send me a text message, please start off with give me your first and last name and what class you're in. Otherwise, because I don't throw the texts away, I use them as a record. Otherwise, I have to sometimes scroll up 10 pages of text to find out what your name was and what class you're in, and that's just a waste of my time. So please just say, hey, this is Billy Younger from PHY 241 N02B or something. Just say that. That's not your section, by the way. Your section is O01B. But anyways, just make sure you let me know who you are when you send me that text message, and that'll make it a little easier for me to reply to you. Otherwise, I have to waste a lot of time finding out who you are so I can make sure I'm answering the right question. Because sometimes one section will be doing something slightly differently than another section. So that's it. That's lab four, or excuse me, that's lab module four for the Thursday lab, and this is all you should need. Thanks for coming, everyone. Have a good day. I hope this might be another chance for anybody to ask questions, but no one came this time, and that's okay. I'm not browbeating you or anything. It's perfectly acceptable for you to just watch this at your leisure. So have a good day. Have a good weekend, and hopefully I will be finishing up the grading your test today, and hopefully I'll also grade at least one lab report today, or definitely by Monday. And just keep an eye out for that, and keep an eye out for announcements and things like that. Like I did last night, I did make an announcement that the online test dates were going to be changed so that we can fit in a couple more online tests prior to face-to-face test two. So have a good day, everyone. Thanks for coming, and bye-bye.